Hi everyone, welcome back. We're going to be talking about indeterminate forms and L'Hopital's rule. So on screen here you have the process or the theorem that we're going to be using for applying L'Hopital's rule. This says that suppose f and g are differentiable and g prime is not equal to 0 on an open interval I that contains A except possibly at A. Furthermore, we want to suppose that the limit for f of x as x is approaching A is equal to 0 and the limit as x is approaching A for g of x is equal to 0. Or we could also say that the limit as x is approaching A for f of x and for g of x could be either positive or negative infinity. Then what we get when we're doing this is that if we apply the limit into those functions, or let's say apply the limit for the ratio of the functions, if we get an indeterminate form, and that's where the previous definition, or that's where the previous theorem was saying, or sorry, not the previous, preface for this theorem was saying, that if the limit is equal to 0, both numerator and denominator, then what we can do is we can apply L'Hopital's rule, and L'Hopital's rule is going to allow us to take the derivative of the numerator and take the derivative of the denominator independent of one another. In other words, we do not apply the quotient rule. And we apply the derivative independent of one another. Therefore, if the limit on the right hand exists, or it's either positive or negative, then we found the limit. Now, the most important aspect of this, yes, of course, is going to be applying L'Hopital's rule. However, we have to try to figure out when is it appropriate to use L'Hopital's rule. Well, according to the theorem, we either need, and again, we need 0 divided by 0 or some form of infinity divided by infinity. Okay, so that's what we need. And again, this could be positive infinity divided by negative infinity. At the end of the day, we just need it to be in that indeterminate form. Once we get that indeterminate form, then we could apply L'Hopital's rule and we can extract the limit that we're observing. There will also be two other indeterminate forms, or in this case, indeterminate products and indeterminate differences. These indeterminate products, or these indeterminate differences, if we analyze or if we see that our limit will get us an indeterminate product or an indeterminate difference, then we must use an algebraic manipulation. So again, anytime you get an indeterminate difference or an indeterminate product, use some type of algebraic manipulation so that we can use L'Hopital's rule. Because if we get an indeterminate difference, we'll be able to perform some algebra to get us into either 0 over 0 or infinity divided by infinity. Same thing for the indeterminate product. There has to be a way for us to do some manipulation, some algebraic manipulation, for us to arrive at 0 divided by 0 or infinity divided by infinity. And finally, we have these indeterminate powers. These indeterminate powers are going to be of the form of 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity. And as you can see on the screen, this says that if we have an indeterminate power result, then we must use a logarithm and an exponential manipulation. What does this mean? Well, this means that we now have to apply these inverse properties that we've learned about these exponentials and these logarithms. So on screen here at the bottom of your screen, I have here that I am starting off with the expression 3x minus 5. if I apply the operation of a natural log and the operation of its inverse composed with one another, then I get that e to the power of natural log of my initial quantity, 3x minus 5, is still equal to 3x minus 5. And again, that's perfect because we have now manipulated this initial expression, 3x minus 5, to have some sort of exponential and some sort of logarithmic function. Same works the other way around. If we take the natural log of the exponent, or in this case, e to the power of 3 to the power of x minus 5. So again, anytime that we have these indeterminate powers, we must use a logarithmic and exponential manipulation to arrive at the limits that we can evaluate. So what I want to work on here is going to be these examples. I want to find this limit on the left. This says that the limit as x is approaching 4 for the function of x minus 4 all divided by x squared minus 16. Now, some of you might be looking at this and you might be saying, well, that can factor. And you'd be right. It does factor and it does simplify quite nicely. However, we want to implement L'Hopital's rule. But in order to implement L'Hopital's rule, we need to verify that we get an indeterminate form. So we're going to go with a direct substitution. So here, again, I'm just going with direct substitution. So a direct substitution, I get 4 minus 4 divided by 4 squared minus 16, which once again leads us to 0 over 0. This is the indeterminate form that we want. Oops, here we go. My apologies, I misspelled that. And I misspelled it again. So this is the indeterminate form that we want. And it's a good day once we get there. So once we get there, what I'm going to do is I'm actually going to perform the limit now. But check this out. I'm going to perform the limit and I'm going to let whoever's going to read my work, I'm going to let them know I'm using L'Hopital's rule. And the way we let them know is by writing LHR as an abbreviation for L'Hopital's rule. So L'Hopital's rule then says, well, we have an indeterminate form, awesome, so we can take the derivative of the numerator. The derivative of the numerator with respect to x, well, that's just going to be 1. Derivative of the denominator with respect to x, that's just going to be 2x. And we can evaluate at this point in time, limit as x is approaching 4, for 1 divided by 2 times 4, which will then get us, oops, my apologies. Geez, I'm not sure what's happening here. There we are. Sometimes we have our off days or our off times. It happens every now and then. Okay, so we're now left with 1 divided by 2 times 4, which will then naturally just get us 1/8. And if you try to evaluate this limit by using factoring, you will have arrived at the exact same spot. Great. Now, looking at part B, again, what we want to do is we want to verify that we can use L'Hopital's rule. So one thing that you want to avoid is using L'Hopital's rule all the time, because L'Hopital's rule does not apply for every single function. So let's check to see if it applies here. Well, I need a direct sub. So let's go with a direct substitution. This is going to be tangent of 3 times 0 divided by sine of 2 times 0. Tangent of 0 is 0, sign at 0 is 0. Therefore, once again, we have arrived at the indeterminate form. And again, we're happy about this. We're good because now that we can see that we can apply L'Hopital's rule, or that we have arrived at indeterminate form, we can apply L'Hopital's rule. And again, I'm going to apply L'Hopital's rule, but I have to take the derivative of the numerator independently from the derivative of the denominator. So taking the derivative of the numerator, I will get 3 times secant squared times 3x divided by 2 times cosine of 2x. Just like that. Okay, so let's see. Let's try a direct substitution at this point in time. If by any chance direct substitution gets us another indeterminate form, then we go back and we try L'Hopital's rule once again. We can keep on repeating L'Hopital's rule as much as we'd like until we get the evaluation of the limit, so long as we can verify that we can keep using L'Hopital's rule. So we're going to evaluate 3 times secant squared. So 3 times secant squared at 0. So that's going to be 3 times secant squared at 0 divided by 2 times cosine of 2 times 0, which will be 0. So let's see. Secant is 1 over cosine. So if 1 over cosine, the argument is 0, that's cosine at 0, but cosine at 0 should get us 1. Therefore, secant squared is just going to be 1. Cosine at 0, once again, that's 1, which means we're left with 3 halves. There we are. It's looking pretty good so far. Okay, not bad. Not bad at all. And we're going to keep going. So I want to now do part C. And we're going to check part C out. Let's see the limit as x goes towards infinity. And this is going to be for x plus x squared divided by 1 minus 2x squared. Okay, let's do a, we can try to do a direct substitution. If we do a direct substitution here, the numerator, we get infinity plus some infinity squared. And again, try not to interpret this as infinity. Try to interpret it more as you're analyzing what is happening to this function as your x values are getting extremely large. So if we take an extremely large number, say like x, plus add it to the square of another really large number, then that addition gets us a really large number. So we then get infinity in the numerator. Denominator is going to be very similar. 1 minus 2 times that really large number squared. Well, in this particular case, since we're subtracting that initial term, then that's going to be negative infinity. However, this is still an indeterminate form. And it's still the type of indeterminate form that we want to see. Because remember, at the very beginning, I stated that indeterminate forms where we can apply L'Hopital's rule is 0 over 0 or some type of infinity divided by infinity. Whether the signs be positive or negative, doesn't matter. So now that we have this, we can apply L'Hopital's rule. So let's go through and let's apply L'Hopital's rule. So the limit as x goes towards infinity. Derivative of the numerator gets us 1 plus 2x. The derivative of the denominator will then get us negative 4x. We can try a direct substitution again. If we try that direct substitution again, we still wind up with infinity over negative infinity, which again is still indeterminate form. Well, that's pretty good. So because we get another indeterminate form, we can apply L'Hopital's rule again. So the limit as x approaches infinity. Numerator, derivative, that's going to be 2. Derivative of the denominator, it's negative 4. Which means the limit of this constant is just going to be the constant of negative 1/2. And that's all there is to it. Again, you must verify if you can use L'Hopital's rule. If you can, apply it. If you can't, then try to manipulate it so that you can use it. Let's look at part D. So for part D, we're going to have the limit as x approaches infinity for x times sine of pi divided by x. Okay, so here we go with this one. Again, some of you might be saying, well, we might be able to use maybe some sort of squeeze theorem here. Okay, yeah, great. We might be able to. However, let's check to see if we can use a direct substitution first. If we can use a direct substitution, we'll try to see if we can, get something out of here. So, as x is going to approach infinity, my first factor, which is x, will be approaching infinity as well, which means I will have some form of infinity multiplied. Let's see this one here, sine of pi divided by x. Well, as x gets very large, pi divided by x is going to get very small. If your denominator grows faster than your numerator, then that value or that fraction or that ratio will be approaching 0. So this argument of pi divided by x is approaching 0 as x gets very large. Therefore, sine of that argument, which will be practically 0, will then just be 0. And we have that one spot. Now, at this point in time, this is what we call an indeterminate product. And according to the process for an indeterminate product, we now have to use some sort of algebraic manipulation. Okay, so here, again, I got a worried face. Might be some issues, but we can algebraically manipulate this. So I am not applying L'Hopital's rule just yet. I'm going to perform an algebraic manipulation. And let me know. Wow, if we were in class, I would say let me know if you agree with this, but since we're not really in class or face-to-face, I will say this. If you have an issue with this, send me an email and we'll discuss it. But as it stands right now, looking at this particular function now, sine of pi divided by x, all divided by 1 over x, this actually simplifies to be x times sine of pi divided by x. So again, all I did was take an algebraic manipulation and I divided both numerator and denominator by 1 over x. Therefore, if I can try a direct substitution at this point, so let's try that direct substitution. Again, as the argument for sine tends to infinity, as the x value for the argument tends to infinity, pi divided by x tends to 0, therefore sine at 0 will be 0. X tends to infinity for my denominator here. That means my fraction 1 divided by x is going to tend to 0. And therefore, we have the indeterminate form that we love, because now we can use L'Hopital's rule. So let's go through and let's start applying L'Hopital's rule now. Okay, here it goes. L'Hopital's rule. Take the derivative of the numerator. Okay, so taking the derivative of the numerator, we're going to, let me write the limit here. We're going to take the derivative of the outside, which is sine. Okay, so derivative of sine, that's going to be cosine of pi divided by x. Again, we keep that the same. And then we take the derivative of the inside function because of the chain rule. Well, the inside function is pi divided by x. And I'm going to do some scratch work on the right-hand side here. It's pi divided by x. In other words, it's pi times x to the power of -1. So if we take this derivative, then what we get, drop the exponent forward. Cheese and crackers. There we go. Drop the exponent forward. There we go. And then subtract 1 from the exponent. Which means what we will get for my coefficient, or my value that's multiplying by the chain rule, is going to be negative pi divided by x squared. That's part of the chain rule. Now when we take the derivative of the denominator, well, taking the derivative of the denominator is going to be very similar to what we did here without the constant. That's going to be -1 over x squared. And look at this now. Negative x squared, well, they should simplify. And we should now get the limit as x is approaching infinity for pi times cosine of pi divided by x. And once we do this direct substitution, as your x values tend to infinity, pi divided by x is going to tend to 0. Therefore, cosine at 0 is 1, and we will be left with pi times 1, which is just pi. Look at that. That is looking awesome. Okay, so pretty good so far. Let's keep going. So that was part D. Now we want to work again with the same process. So I'm going to just start a new section here of examples. And we want to find the limit. Part A. Let's work with the limit as x is approaching 0 for cosecant of x minus cotangent of x, and we'll see what happens. Okay, so let's try a direct substitution first, because again, we always want to get direct substitution. Always try direct substitution first. If it works, awesome. Then you don't need to apply L'Hopital's rule or anything like that. So in a direct substitution, we will get cosecant of 0 minus cotangent at 0. Now, cosecant at 0, well, cosecant is 1 over sine, and 1 over sine at 0 is going to be 1 over 0. And if your denominator is 0, or let's say if your denominator is approaching 0, then we naturally get that that overall fraction will tend to infinity. Cotangent at 0. Well, cotangent is cosine divided by sine. Cosine in the numerator, cosine at 0 will get us 1, but the denominator sine at 0 gets us 0. So as x tends to 0, that overall fraction is going to tend to infinity. Now, please be very careful. Infinity minus infinity is not 0 unless you can prove it. But this is good for us because this tells us that this is an indeterminate difference. And again, kind of like my worried face there, since we got an indeterminate difference, that's going to be okay. We are going to be able to algebraically manipulate this, or let's say trigonometrically manipulate this, to arrive at the indeterminate form that we need for L'Hopital's rule. So let's see if we can do some algebraic or some trigonometric substitutions here, or some way of manipulating this. Again, cosecant of x is 1 over sine of x. Cotangent is cosine of x divided by sine of x. Look at the denominators. They're both the same. Therefore, we get the limit as x... Wow, I put approaches infinity. I am really having an off day. My apologies. As x approaches 0, numerator now becomes 1 minus cosine of x. Denominator is just the sine of x. Now that I've condensed these terms into one fraction, I want to approach direct substitution again. Let me see if anything has changed so far. So, making my substitution, 1 minus cosine at 0, well, that's just going to be 0, so that's pretty good. Divided by sine of 0, well, that's 0. Wow, look at that. Things did change. This is the indeterminate form that we like. Happy. Therefore, we can apply L'Hopital's rule, and once we apply L'Hopital's rule, derivative of the numerator will then get us sine of x. The derivative of the denominator will then get us cosine of x. And in doing so, we can now make the substitution, and we get, or we can just call that tangent. We get tangent at 0, which is 0. Great. Again, everything worked out real nice for us here. So as we've seen, we can get some indeterminate forms, or these indeterminate products, or these indeterminate differences. Whichever one that we arrive at, we should be able to work with it. So let's go on to part B. So let's look at part B here. And for part B, we want to look at the limit as x is approaching 0 for the function of 1 minus 2x to the power of 1 divided by x. So again, try direct substitution first. So direct sub, let's try that. As x is approaching 0, the inside of the parenthesis will be 1. The the exponent, as x tends to infinity, for my fraction of 1 over x, that overall fraction is going to get extremely large because the denominator is heading towards 0, which means we will have 1 to the power of infinity. Now, I know what some of you all might be saying, well, 1 to the power of almost any number gets us 1 itself. And that is kind of deceiving. Okay, that is kind of deceiving. So, again, we're not having 1 to the power of a number. We're having 1 to the power of infinity. Infinity isn't a number itself. It's this concept that we use to represent the values that we keep on approaching. So as soon as we find out a large number, we keep going and we approach the larger numbers. So let's go through now and let's extract. What type of form is this? Well, this is an indeterminate power. Oof, more of a sad worried face there, because now we have some legwork to do. Okay, so we have some legwork to do, and we're going to go ahead and work this out as much as we can. So here we go. What we want to do is we want to use some sort of natural log and natural base manipulation. What that means is I'm going to look at my function here, the function of 1 minus 2x to the power of 1 over x. I'm going to look at that function and I'm going to want to interpret it in a different way using my natural log and my exponential function. So follow me on the right hand side of the screen and we're going to see what we're going to do here. And actually, I'm not going to separate the screen. It's okay. So what we're going to do here is we're going to start off by saying that I have my function, call this y, which is 1 minus 2x to the power of 1 over x. Now, if we apply the natural log onto both sides, then we get the natural log of 1 minus 2x raised to the power of 1 over x. But by properties of natural logs, exponents can move forward and multiply the natural log if the exponent belongs to the overall argument of the natural log. In this case, it does. So we get 1 over x multiplied by the natural log of 1 minus 2x. Okay, not too bad. Now, in order to undo this natural log on the left-hand side, I'm going to apply the power of e. So e to the power of natural log of y is equal to e to the power of 1 over x multiplied by the natural log of 1 minus 2x. So this is now very beneficial because on the left-hand side of that equation, we are now left with y. On the right-hand side of the equation, we're now left with e to the power of 1 over x multiplied by the natural log of 1 minus 2x. And this is where we want to be. We want to be here more specifically because when we're doing this, we can now apply a limit. Now, before we move forward, I'm scrolling up to where I showed that we were having this logarithmic or exponential manipulation like I showed on the screen here, towards the middle of your screen. Using what we had, or using my function here, I can take the natural log and then I can undo that natural log by composing it with the exponential, essentially getting to this point here. Now, this is what I want and this is where I want to be. Because now, as I'm going to take the limit as x is approaching 0, notice my function, and I'm going to highlight this in a different color, my function, which was 1 minus 2x to the power of 1 over x, that was this function on the right-hand side of your screen. which we said was equal to y. But then we manipulated this using logarithms and exponentials to arrive that that same function is equal to e to the power of 1 over x multiplied by natural log of 1 minus 2x. Which then leads me to what I was saying on the left-hand side of your screen, that instead of writing 1 minus 2x to the power of 1 over x, I want to write e to the power of 1 over x multiplied by the natural log of 1 minus 2x. And again, these two equations are equivalent, or I should say these two functions are equivalent. And now this is beneficial because I can now start identifying that as the limit of x is approaching 0, for e to the power of this big function, well, the exponential function e is a constant. Therefore, the limit transcends the constant function, or the constant base, or in this case the natural base, and we get to take the limit of the exponent in order to identify what is this limit going to be. Well, that's great, because now all we get to do is evaluate that limit, and that's not too bad. That limit shouldn't be bad at all, or it might be, but we'll get to it. So let's go ahead and let's keep going then. Let's try a direct substitution now. So try direct sub. Now that we've manipulated so far. Okay, so we're going to get e to the power of, let's see, 1 divided by x, as x tends to infinity. Then this is going to be some form of infinity multiplied by natural log of 1. So natural log of 1 is going to be 0. So check that out. The exponent is now an indeterminate product. Okay, so starting to get a little bit better. Since it's an indeterminate product, we can algebraically manipulate that exponent in order to evaluate that limit. Well, let's go through. Okay, so what I will have at this time, I want to have the natural log of 1 minus 2x, and there doesn't seem to be a lot that I can do here besides just distribute the x into that natural log. Now I'm not distributing it into its argument, I'm only distributing into the overall term. So as I take the limit here in this direct substitution, I now get e to the power of, well again, numerator, natural log of 1, that's 0, divided by x is approaching 0. Bam, we're there. We get an indeterminate form. Nice. Now we're ecstatic. So we went from an indeterminate power to an indeterminate product to now an indeterminate form. And it is at this point in time that we can now apply L'Hopital's rule. So let's apply L'Hopital's rule to that limit. E to the power of the limit as x is approaching 0. Let's take the derivative of that numerator for that exponent. Derivative of the natural log, well, that's going to be 1 over its argument, which is 1 minus 2x, multiplied by the derivative of the inside, which is negative 2. That's all going to be divided by, that's all going to be divided by the derivative of x, which is just 1. Okay, let's clean this up. E to the power of the limit as x is approaching 0. And here, my function that I'm taking the limit for is just going to be negative 2 divided by 1 minus 2x. So as x tends to 0, as x is going to tend to 0, we're going to get e to the power of negative 2. Wow. So this limit, the limit that we were just looking at for 1 minus 2x to the power of 1 over x, this limit is equal to e to the power of negative 2. Check that out. Isn't that awesome? Now remember, we said, hey, it's not exactly 1 because, again, the exponent for 1 to the power of infinity, infinity is not a number here. Infinity is just this concept that we keep approaching. We're just sending all these x values or all these values to infinity, and they're just going to keep growing larger and larger and larger and larger. And at that point in time, we cannot figure out what the limit is unless we manipulate it to get something that we can evaluate. So this is the process of L'Hopital's rule. Now, what I want you all to do is work on these problems. On the exam, I will almost guarantee that you will get an indeterminate power type of question. So please be very mindful of that I need to see the work going into this. And if you structured your argument very similar to mine, you're going to get full credit. Okay, so just keep that in mind. But if you have any questions, again, feel free to reach out to me. So I hope you all enjoyed this lesson, and I hope that you all stick around, and we will be talking about separable differential equations on the next video. So till next time.